Hello my dear students. In these videos we are talking about vectors. We are talking about vector functions. So one of the main applications is that with vectors you can define particle moving along a curve, right? Or you can define a path. Suppose you have a path like this, right? So I can have equation of the path as follows, that this is my path, right? This is the path, and this is actually a function from a b some interval to r cube, right? For example, if you have x from this can be r cube or r square. Okay, for example, if we have 0 to 2 pi, we have a function to r square which is r times cos theta. Okay, this is my theta, and r times sine theta, right? So x is a vector valued function. Can you see? So this is a circle, this is a circle, this is a circle. So we will be talking about length of a curve when we are dealing with vectors, like how we can find length of a curve if we know the equation of the curve in terms of vectors. So let me write down the problem statement. What we are trying to do here is we are given a curve's equation in terms of a vector which we denote it as xt vector, which is some component x1 I cap plus x2 j cap plus x3 k cap, right? So basically we can also write it as x1 comma x2 comma x3, which is in the component form if we want to avoid I cap, j cap and k cap, right? Then I would like to know the length of the curve, Now you see your curves points, they are parameterized by t. So you want to know what is the length of the curve from t equal to a to t equal to b. Does that make sense? Okay, so for example, if my curve is, right, suppose I told you that we can take this example of circle, right? And suppose you have this circle, this is 0 to 2 pi, and then it is going to cos theta. R is suppose 2 cos theta or 2 sin theta, right? And then suppose, so I know that this is the curve I am talking about. Okay, so I can write it as t so that we are consistent. Suppose this t is our time or anything, right? So this is my t and x is a function. So this is my x vector, right? I should write it as x of t vector, right? And suppose I want to know the length from 0 to pi by 2. So I want to know what is this length. What is this length? In this case, it is very easy because we know the formula for circumference and it is 1/4. But suppose you have some, 0 to, let us take from A to B. You have a curve from A to B, some function which is some weird looking function, and the curve is something like this. And suppose you want to know the length from A to some point C, right? So what is this length? Okay, so we will not be able to use simple formulas like we can use here in case of circles. So here we would like to have some formulas, right, which will help us in finding the length of any kind of curve. So let us look at that formula. I hope you understand the problem statement. So what are the assumptions I am taking? I am saying that x from AB to r cube or r square, or you can have any Rn, right? You can go to 4 dimension, you can go to 5 dimension and so on. Be a C1 path. Okay, so you should not be scared about, sometimes I have seen students, they are scared when they see this C1, C0. They are very simple terms. If you, let them scare you, then you will be scared of them forever, right? So just learn them. It's very simple. C1 is a class of functions. It means that the function is continuous. The function is continuous as well as its first derivative is also continuous. First derivative is also continuous. Why do we need such a condition? We need these conditions for, for length to actually make sense. First derivative continuous means you have smooth curves. For example, if you look at this curve like this is a curve, this is a C0 curve because it is a continuous function, you can see. But if you look at the first derivative, it is not continuous at this point. So this is a C0 curve. Something like this is C1 curve. It is smooth without any corners. Okay, so it's simple. Why we are putting this assumption of C1 curve? So that we actually know that what we are calculating makes sense. Length makes sense, right? Okay, so let us see how we will calculate the length. So idea is, suppose this is my curve, this is my starting point A, and this is my end point B, and x from AB to this x function, x vector, right? So let me call it as xt, right? It can be any dimension. It can be 2-dimension, 3-dimension vector, or n-dimensional vectors. So what I have to do, this is my t, right? So t is from A to B. I have to break it into parts. So I'll say this is a partition of t. Partition of t I'm going to do. So what I'll do, I'll call t0 as A, and then I have t1 less than t2 less than tn equal to b, right? So I have these partitions, and corresponding I have the point x of t0. This is my x of A because the curve is x, right? Then I have x of t1, then and so on. I have x of tn, which is x of B, and this is x of A. So I have these points like this. This is x of t1, then the next point is x of t2, next point is x of t3, next point is x of t4, next point is x of t5, next point is x of t6, next point is x of t7, and so on, right? Now what is my aim? I want to find out the length. So looking at this diagram, can you think about a method which can give us the length? You look at this diagram and think of a method which can tell us the length. Take a moment. Maybe you can pause a video for a minute and then you can figure out, and then you can come back. So idea is, you join this point with this point. Let me take this a different color. Let me take a black color. So this is the line, and then join this point and this point. This is the line. Then this point and this line, and this point and this line, this point, this point, this point, and so on, right? So can you see I have these straight lines? You can look at the straight lines. Can I approximate my length? I can add all these straight lines. So if we call the length of a small segment, first look at the length of the small segment, call it x of ti minus x of ti minus 1. Can you see? For example, this is x of t0 minus t1 minus t0. Then the next length is x of t2 minus t1, and so on, right? And you call it as del of si. Okay, so the length of small portion. So basically what I'm saying here is, let me explain again. So you start from x of t0 and then you go to x of t1, right? This length is your del s0. Then further you have a length which is del s1. Then further you have a length which is del s2. Then further you have a length which is del s3. Further you have a length which is del s4. Further you have a length which is del s5. And then further you have a length which is del s6, and so on, right? Now if I add all these segments, I will get an approximation to the length of my curve from A to B. So what we are saying, that length can be approximated with this sum I from 1 to n delta of Si. Okay, so you can take it to be, we have to start from, okay, I'm calling it as Si, right? So I'll start I from 0 Oh, okay, I'm sorry. I have to start from SI is starting from 1, right? Then only it is xt1 minus xt naught. So this is correct. Okay. So this is the approximate length. Now if I want to make it, and what is del SI here? Del SI here is x of ti minus x of ti minus 1. And this x is C1 function. That means it has a continuous derivative. So do you know mean value theorem? See, all the mathematics come into, it's like a puzzle. When you try to fit all the bits and pieces, you get a very nice picture. So here we are going to use mean value theorem. So what mean value theorem tells us? That this is equal to, suppose, let us write its components, right? So that it's easy for us. Let us write that xt is, there are 3 components. Suppose this is capital, okay? So that we can make a distinction. So 3 components, I'll call it as xt, yt, zt, right? So this will be del si would be, let me first do like this. So if I give 3 components to xt, just a minute, I'll apply the mean value theorem in a moment. Then what will be my xt del si, which is x of ti minus x of ti minus 1. That would be xti, comma yti, comma zti minus x of ti minus 1, comma y of ti minus 1, comma z of ti minus 1, which is equal to x of ti minus x of ti minus 1, comma y of ti minus y of ti minus 1, comma z of ti minus z of ti minus 1. I can write like this. Now on these 3, you apply, these are C1 functions because x is a C1 function. So this is a C1 function. This is also a C1 function. This is also a C1 function. That means its first derivative is continuous. So we can apply mean value theorem. So you apply mean value theorems here. Mean value theorems. So what does that say? It says that this quantity is equal to x derivative at ti star, where ti star is a point between ti minus 1 and ti, times delta ti, where delta ti is ti minus 1. And similarly, this quantity here, let me change the color. This quantity here is y prime ti, this is some other point, del double star times del ti, okay? And similarly, this quantity here is z derivative ti triple star, comma del ti, right? So this is your del si. Okay, it is actually the magnitude, right? Because del si is the length, so length has to be the magnitude, right? Okay, so we'll take magnitude everywhere. Okay, now you know that given a vector how to find the magnitude. So this would be, magnitude is the x component square plus y component square plus z component square. So x component here is x prime ti star times del ti square, plus y component is y prime ti double star times del ti square, plus z component is z prime ti triple star times del ti square, right? Now this is my del si. Del si would be, I can see this would be x dash ti star square plus y dash ti double star square plus z prime ti triple star square. What I am doing is, I am taking these terms common. So out of the square root sign, it will come at times del ti. So this is my del si. And I was saying that my L can be approximated with some I from 1 to n del si. So that means this length can be approximated some I from 1 to n square root of x dash ti star square plus y dash ti double star square plus z prime ti triple dash triple star square del ti. And now we don't want an approximate length, we want an exact length. So when is this approximation going to be exact? When you have very small chunks, right? If you take very small pieces, right, very small tiny pieces, infinite pieces, then you are always moving along the curve, actual curve. So if we take infinite pieces, we will get the actual length. So length is equal to limiting case. What is the limit we are going to apply? That this del ti goes to 0, maximum of del ti goes to 0, right? So you are doing the partition in such a way that the length of the partition is going to be 0. Okay, so when del ti goes to 0, then ti star, what was del ti? Del ti was your ti minus 1 to ti, right? Del ti. And inside this interval are your ti star, because this was a point between these 2 points, and this was also a point. So somewhere here is ti double star, we don't know where it is inside the interval somewhere, and somewhere here is ti triple star. And as del ti goes to 0, so it means that all of these points are going to coincide and they're going to be equal to, say, to 1 point, right? So they are going to merge. So we can write it as square root of, okay, so because they are going to be the same point, so I can just use one variable t, xt square plus yt square prime plus z prime t square. And then when in the limiting case, we also have sum I from 1 to n, and this was del ti. So I should write, when in the limiting case this sum becomes integral. That is the definition of Riemann integration. So this becomes summation xit square plus x prime t square y prime t square z prime t square dt. And then if you want to take from A to B, that is your length. Okay, so this says that if you want to calculate the length, this is the way, this is the formula, right? So if you want to skip the proof, you can do that. But as a mathematician, we should know, right? Just if we do formula based maths, that is not actually a mathematics, right? Anybody, if you tell formula to anybody, okay, this is the formula, can you apply, they can do that, right? But we should know what exactly is the story behind that formula. That is where the fun lies, right? So if you don't want this proof, you can just skip it, but I will highly recommend that you go through this beautiful proof, right? That how we get this formula. So it means that, suppose I have a curve, right, xt, which is having two components, xy, small x and y. Then I can straight away find its length. Suppose a to b, I want to find its length. So this is the formula, a to b, x dash t square plus y dash t square dt, right? And similarly, 3-dimensional, 4-dimensional and 5-dimensional, I can use the same formula for n dimensions. Now if you look at this formula, you can see that, what is this? If I ask you, suppose a particle is moving along a curve xt, yt, zt. Forget about this formula and think about this as a separate statement, and then we'll connect. Suppose a particle is moving along a curve. This is the curve along which the particle is moving. How much distance it travels from t equal to a to t equal to b. So how do you calculate that? You know this is the position vector of the particle, right? So we'll get the velocity vector first. So what is the velocity vector? Velocity vector would be the derivative, as we studied in the last videos, right? And then I'll get the speed. What is the speed? Speed is the magnitude of the velocity vector. And then I will integrate it from A to B, because if I integrate the speed, I'll get my total distance, right? So you see, this formula is same as this formula. This formula here which we derived and this formula here, they are same. So that makes sense also, because if you are measuring the length of a curve from this point to this point, that is same as saying that a particle moves along this curve, how much distance it travels from A to B. Okay, so you can derive the same. You can also use this as a proof that, okay, if I want to find my length from point A to point B, then I assume that there is a small particle moving along the curve, right, from A to B. I'll find out how much distance it travels, and for that I have to find my velocity vector, and then I integrate that velocity vector, right? So this is a simple concept. Now let us do some problems based on this simple concept, right? So question is, so you can extend it, you can extend this concept to any dimensions, to any number of dimensions, to n dimensions. Okay, so now we have this problem that x is a curve from 0, 2 pi to r square, right, defined by x of t is a cos t comma b a sin t. So you clearly see this is a circle, and the question is, find its length. Find the length of the curve. Length of the curve. If they don't specify you the points A and B, then obviously you have to find the length of the whole curve. That means you have to use these points. So we are going to find our velocity vector first, which is going to be minus a sin t, a cos t, and then we are going to find out its magnitude, which is minus a sin t square plus a cos t square, which is equal to a square sin square t plus cos square t, which is equal to a, right? And then to find the length, we have to integrate from 0 to 2 pi of x prime t modulus dt. So that is going to be 0 to 2 pi a times dt. So a comes out, the integration is t, 0 to 2 pi, so you get 2 pi a. So you see, we also know that this is the circumference of the circle, so we got it. That makes sense, I hope. Okay, one last problem for this video, then we are done with this video. So we have another problem for the helix. So you know what is a helix? A cos t, a sin t, comma bt. So this is a curve from, like, in r cube, right? And 0 to 2 pi is the description of t, right? And the question is, find the length. So it's also similar. So what you are going to do? You are going to find out your velocity vector first. That is the derivative of the components with respect to time t. So that would be a sin t negative a cos t comma b. Now then you are going to find out the magnitude of the velocity vector. So that would be a square sin square t plus a square cos square t plus b square. So that would be a square common, inside you have sin square t plus cos square t plus b square. So you have square root of a square plus b square, right? Therefore your length would be summation from 0 to 2 pi, because that is your limits for time t, okay, of whatever is my velocity vector, which is square root of a square plus b square times dt. So you get the length to be 2 pi a square plus b square. So this is the length of the helix, right? So now you understand that how we are going to deal with the problems where we have to find the length of a curve, and that is equivalent to finding the distance traveled by a particle whose position vector is given, right? When you are given the position vector, that means you are given the path along which the particle is making a move, okay? Okay, thank you, dear students. Please share this video, subscribe to this channel, and support my channel by sharing the videos. Okay, if you have any comments, please write in the comment box. Thank you. Happy learning.